All right, let's talk about null hypothesis significance testing, also known as NHST for short, also known just as simply hypothesis testing. This will be the first in a series of at least 3 videos, and who knows, maybe there'll be more sequels than that even, but to keep these from going on for like 9 hours, I have to break them up into pieces. But this will be the first one, so this is my very first introductory video to hypothesis testing for people who really don't yet have much grasp of hypothesis testing. So you're relatively new to statistics and you're brand new to hypothesis testing. Let's see if we can get you going here. Alright, so to illustrate hypothesis testing, we're going to start with the simplest possible experiment, flipping a coin. Now remember a few things about probability. First, the set of all possible outcomes of an experiment is the sample space, which we symbolize with the letter S. And the first axiom of probability is that the probability of something from the sample space happening is 1. Or in other words, if we do an experiment, something's got to happen. So, in the experiment of flipping a coin one time, the sample space has just 2 events, heads and tails, and each has the same probability if the coin is fair. And a probability is exactly 0.5 for each of those events. And then the probability of heads or tails is the same as the probability of the sample space, since those are the only events in the sample space, and that probability is 1. Now, so in the experiment of flipping a coin one time, the sample space has just 2 events, heads and tails, each has the same probability. Now I can divide the sample space into 2 sets of events, and I can give them names. I'll call one the null hypothesis, and I'll call the other one the experimental hypothesis. You might call it the research hypothesis, or the alternative hypothesis, or the alternate hypothesis. So one's the null, and then one has a few dozen names. Lots of people call it lots of different things. I'm just going to call it, for the most part, the experimental hypothesis. For the null hypothesis, we're going to use the symbol H sub 0. That's this one right here. We actually say, though, usually H naught to make ourselves sound British and sophisticated, so people know that we're serious people. H naught. So H naught is our symbol for the null hypothesis. For the experimental hypothesis, as I said, also sometimes called the alternative hypothesis or the research hypothesis, we'll use H sub 1. And we'll usually just say H1. But understand that we mean H sub 1. For flipping a coin one time, I might have a null hypothesis. The coin will land heads, and my experimental hypothesis is maybe the coin will land tails. There's really not any reason to give the hypothesis in this experiment those labels because the experiment is so simple. But I want you to get used to the idea of dividing up the entire sample space into 2 sets. And notice 2 other things about these sets. First of all, they are exhaustive. In other words, they cover every event in the sample space. In other words, there's nothing left in the sample space that's not falling under one of these 2 sets. The one that I'm calling the null hypothesis and the one that I'm calling the experimental hypothesis. And also, they are mutually exclusive, which means if an event in one set happens, that implies that no event in the other set also happened. So, we split the sample space into 2 sets, 2 subsets. One we label H naught, the null hypothesis. One we label H1, the experimental hypothesis. And those 2 sets are mutually exclusive and exhaustive of the sample space. Now, the null and experimental hypothesis for a single flip aren't really very interesting. And in the end, we can't really make any inferences about the coin. So let's make it more interesting by flipping the coin twice. Now we can ask things like, is the coin a fair coin? If it comes up heads or tails too many times, maybe it's not a fair coin. Maybe it's a trick coin. To figure it out, let's look at the sample space for the experiment of flipping a coin twice. So we might get heads on both flips. Or we might get heads on the first flip and tails on the second. Or maybe tails comes up first and then heads. Or maybe tails comes up both times. So just take a second to verify for yourself that nothing else could happen in the experiment. Flip a coin twice in a row. This is the entire sample space of that experiment. So now, what if I make a claim? I claim that the coin is biased to come up heads. In other words, it's not a fair coin. It's a trick coin. How could I decide? Now, for those of you who are eavesdropping, who already know that we can't with this experiment, shh, stay tuned. It's coming up. But for the rest of you, we're going to try to figure out with this experiment whether or not we're dealing with a fair coin or not. All right. So, since we are not addled philosophers, we will assume that there is a reality, a truth about the coin. And we want to make a decision about the coin. So that gives us two possible states of the world and two possible decisions that we can make. And so we illustrate that with this little matrix here, right? States of the world, either it's a fair coin or it's a biased coin, and the decision that we make. We're going to decide that it's either a fair coin or a biased coin. And this matrix here we call a decision matrix. All right. So we'll call the fair coin state of the world the null hypothesis, symbolized with H naught. And my claim that the coin is biased we'll call the experimental hypothesis, or H sub 1. So if the coin is fair, and we decide it's fair, then what we have done is we have failed to reject the null hypothesis. If the coin is biased, but we decide it's fair, well, then we've made a mistake. And we call that mistake a type 2 error. It's a false negative. If we were diagnosing an illness, this would be seeing a sick patient and saying they were okay, that they weren't sick. If the coin is actually fair, but we decide that it's biased, that error also gets a name. We actually call that one the type 1 error. And in science, it's considered the more serious error because it leads scientists to believe something that is false. Whereas a type 2 error just leaves us in ignorance, which was the state we started out in anyway. So at least we're no worse off if we get a type 2 error. We may still be ignorant of the of the facts, but we're no more ignorant than when we started off. A type 1 error, though, that actually introduces error into the scientific record. Now scientists believe something that is false. So it's considered the more important one to guard against. Okay, now the reason that the type 2 error leaves us in ignorance, I won't actually get into in this video. Just briefly I'll mention it's because we never actually decide the coin is fair. We just fail to decide that it's biased. But in most experiments, a failure to reject the null does not lead us to conclude that the null hypothesis is true. All right, anyway, so that type 1 error is a false positive. If it were a patient that we were trying to diagnose, the patient would be healthy, but we would be saying that they were sick. So finally, if the coin is biased and we decide it's biased, we have made a discovery. The probability that we will be able to detect the bias in the coin is called the power of our statistical test. And yes, I'll do a video on that at some point. Probably by the time you're watching this. Alright, anyway, time to get started testing. Remember that what we do is we want to divide the sample space into two categories that are mutually exclusive and exhaustive. Mutually exclusive meaning if one set happens, the other set cannot have happened. And exhaustive meaning that there's no event in the sample space that's not included in one of the two sets. For my claim, it probably makes the most sense to pick heads on both flips as the part of the sample space that is consistent with my claim that the coin is biased to come up heads. So this is the part of the sample space that is consistent with the experimental hypothesis, H1. The rest of the sample space is the part that is consistent with the null hypothesis, or H0. In this case, H0 is that the coin is fair. If it's fair, all these outcomes would be expected. So, what's the probability that we would get an outcome consistent with the experimental hypothesis? Well, remember the definition of probability. A probability of an event A is just the number of things that are A divided by the total number of things in S, the sample space. And how many total events are in our sample space? Well, there's 4. And how many of those events are classifiable as consistent with the experimental hypothesis? Well, in this case, just 1. And so that gives us our probability of getting heads on both flips of the coin. It's 1 out of 4, or 0.25. Now that probability is called the p-value, and p-value, that's an important term to learn. Technically, the p-value is the probability of getting a result as extreme or more extreme than the one you actually got. More extreme doesn't make much sense in this example since the experiment is so simple. You can't get more than 2 heads in a row in this experiment. But more extreme will be a very important concept in just a second. So suppose I actually do this experiment and I actually get 2 heads in a row. Can I conclude then that my coin is biased? Well, it turns out no. This experiment doesn't have enough power to do that. So first, even though I labeled that part of the sample space as consistent with the experimental hypothesis that the coin was biased, it's still consistent with the null hypothesis that the coin is fair. It would happen 1 in 4 times if the coin was fair. That's something important to understand too. Really important, actually. The p-value that I calculated is the probability of getting this result if the null hypothesis is true. In other words, it's the probability of the data given that the null is true, or given the null hypothesis. In still other words, assuming the null is true, I would get heads 1 out of 4 times that I did this experiment. What's the probability of getting heads if the null is false and my experimental hypothesis is true? Well, we actually can't know that unless my experimental hypothesis specifies it. We can do that sort of thing, particularly in Bayesian analysis, but that's another topic for another video. Actually, I think by the 3rd one in this series, I will be talking about Bayesian statistics a little bit. All right, but here I don't do that. I just said the coin was biased, but the only probability I can get in null hypothesis significance testing is the probability of a given outcome if the coin is fair, or in other words, if the null is true. So, how weird does an event need to be for me to reject the null hypothesis? Well, in the biomedical and social sciences, we usually say that it has to be so weird that it would happen only 1 in 20 times if the null is true. So that translates to a probability of 0.05, or a 5% chance. And we call that criterion alpha, and of course symbolize it with the Greek letter alpha. And since our experiment of flipping the coin twice can only produce p-values as low as 0.25, our experiment actually won't allow us to conclude that the coin is biased. We would have to flip more times to figure that out. How many more times? Well, what if we flip it 3 times and it came up heads all 3 times? Would that allow us to decide that the coin is a biased coin, a trick coin like I claim? Now, going forward, listing all the possible outcomes of an experiment is going to get really hard and take a really long time. In fact, after about 7 or 8 flips of a coin, it's just going to get completely impractical. So we'll do it one last time for this experiment, but we'll also go back to the axioms of probability to figure out some of those probabilities so that you can make the connection between the axioms and the probabilities. And after that, we'll just use the axioms without listing all the possible events in the sample space, because that's just going to get really, really tiresome. All right, so here are all the possibilities and the multiplication rule, which was one of the axioms you remember of probability. The only other thing you need to know is that we can chain the multiplication rule as many times as we need. So what's the probability of getting 3 heads in a row? Well, it's just the probability of getting heads on the first flip times the probability of getting heads on the second flip times the probability of getting heads on the third flip, which turns out to be 0.125. You can just do that with a hand calculator just to be sure that we got it right. And of course, because we enumerated the sample space, you could also just count the number of events in the sample space that are classifiable as 3 heads in a row. And of course, there's only one of those in this sample space, right? And then the total number of events in the sample space, which is 8. Let's see if I got this right. 1, 2, 3, 4, 5, 6, 7, 8. Sure enough. You might stop the video and confirm for yourself that these are all the possible things that could happen in the experiment flip a coin 3 times. And if you divide 1 by 8 by the definition of probability, you will also get 0.125. There it is. All right, so we got the same answer both ways. That's good. Good to know. So now going forward, for more flips of a coin, I am not going to enumerate the entire sample space. So can we reject the hypothesis that the coin is fair if I got 3 heads in a row on 3 flips of a coin? Well, no, because the probability of that, and the lowest probability that this experiment can possibly produce, is 0.125, which is still not low enough, still not below our alpha level of 0.05. Remember, we have to get a probability of 0.05 or less in order to reject the null hypothesis. So, in this experiment, the most extreme thing that can happen would have a p-value of 0.125, still not weird enough to reject the null hypothesis that the coin is a fair coin. So we still have our question, how many times do I have to flip it? Well, using the multiplication rule, we can find out fairly quickly. Let's try 4 flips. What if we flip a coin 4 times and it came up heads all 4 times? Well, that gives us the probability of getting heads on the first flip, the second flip, the third flip, and the fourth flip. Each of those probabilities is the same, 0.5. By the multiplication rule, and by chaining the multiplication rule, we get the probability of that event happening 0.0625. Still not weird enough to reject the null hypothesis. This would happen about 6 times out of 100. We need it to happen no more than 5 times out of 100 to be so weird that we're going to reject the null hypothesis. With 5 flips, the probability of heads all 5 times is 0.03125. Now that is well below our alpha. Well, I shouldn't say well below. It's barely below. So if that happened, I could actually reject my null hypothesis that the coin was fair and conclude that it was indeed biased to come up heads. Statisticians have a name for a result that is very weird if the null hypothesis is true. They say it is statistically significant. That just means that if the null is true, this result would be very unusual. It would happen less than once every 20 times. It's really weird, but wait, isn't there another weird thing that could happen if the coin was fair? What about 5 tails in a row? A fair coin might, just by chance, also come up 5 tails in a row. Now this brings up the issue of the tails of a distribution, as opposed to the tail of a coin, tails of the distribution and one-tailed versus two-tailed hypothesis tests. Remember my experimental hypothesis that the coin is biased to come up heads. That's a directional prediction. So with that prediction, if I flip a coin 5 times and it comes up heads all 5 times, I could reject the null hypothesis and conclude with the traditional level of scientific certainty that the coin is biased. But if my experimental hypothesis was only that the coin was biased, and I didn't say in which direction, 5 flips would not be enough, because I would have to add the probability of 5 tails in a row to my p-value. That's a two-tailed test. Anyway, back to this decision matrix. If I have a hypothesis that a coin is biased to come up heads, and I do an experiment where I flip the coin 5 times and it comes up heads all 5 times, I can reject the null hypothesis that the coin is fair and conclude that the coin is biased. If I get any other outcome, including 5 tails in a row, which is just as weird, keep in mind, I must fail to reject the null hypothesis of a fair coin, because that outcome fell into the part of the sample space that I was calling consistent with the null hypothesis. But in either case, I'm making an inference. So the hypothesis testing is the logic at the heart of what is called inferential statistics, which is what we do when we take a sample and try to make inferences about the population the sample came from. Now, this video has gone on long enough. You now get the basic idea behind hypothesis testing. Whatever experiment you're doing, you have to know all the possible outcomes of that experiment and the probability of obtaining each of those outcomes if the null hypothesis was true. Here with our coin flipping experiment, we knew the probability of each possible combination of heads and tails if the coin was fair. I'll do a couple of more advanced videos, look for those, they should be up probably by the time you see this, where I elaborate on a couple of these issues. The first is the issue of directional predictions and tails. I illustrated null hypothesis significance testing with a directional prediction and a one-tailed p-value, but one-tailed tests are actually problematic if you have a even if you have a directional prediction. I'll talk about why that is in that future video. Also, I'll do a video on why some statisticians, mathematical psychologists, and probably scientists from other fields think that null hypothesis significance testing is logically invalid and should never be used. And finally, I'll go over an example and explain how we can know all possible outcomes of a real experiment where we measure a continuous variable and calculate its mean. And that will introduce a statistic called the t-test. All right, that's enough for now, so I will see you guys in the next one.